Welcome back, folks. So in this pre-work, we're going to look at a brief introduction to the exponential and logarithmic functions. I'll point out that in this video, I'm not going to go into a very heavy discussion of graphs of transformations of these functions. I will say that if you find this discussion difficult, you might find some previous works helpful. Specifically, the most important one is if you're struggling with this, make sure you go back and rewatch the pre-work introduction to logarithms, and I've hyperlinked to that here. So let's go ahead. We want to look at the exponential and logarithmic functions. We're going to study them graphically first without any transformations, but let's go ahead and just start the good old-fashioned way of working with these functions by building a table of values. So here you can see I've given us an axis. We'll talk about why I sketched this dotted red line here in a minute. But here I've given an axis, and I want you to go ahead and graph the function f of x equals 2 to the x. Now, always with some of these standard functions that you learn in math classes, you want to develop tools for graphing these specific functions. Maybe you've memorized their basic shape. Maybe you're able to keep track of just a couple of key points to graph them. There's various other graphing techniques. But if you're not sure how to first graph a function, the best fallback is to fall back on a table of values method for graphing a function. Now, this is an unsophisticated way to graph a function, and generally it's not good enough after you do it the first time. After you do it the first time, there are better techniques for graphing these particular functions that we study in great detail. So what I'd like to do is let's go ahead and sketch the graph of 2 to the x, assuming we know nothing about it, except that we know how to work with exponentials, and let's go ahead and build a table of values. So I've kind of given you a hint for these table of values here for what we should pick for our domain values, but I'd like to pick x equals -3, x equals -2, -1, 0, 1, 2, and 3. And I'm going to space those out a little bit more. So let's go ahead. I'd like to jump into the middle here. Let's go ahead and evaluate this function f of x equals 2 to the x at the x coordinate 1. So putting in a little more detail than we normally will, I'll go ahead and write that f of 1 is equal to 2 to the first power, and I've learned how to evaluate that. That evaluates as 2. Likewise, if we were to evaluate f of 2, this would be 2 to the second power, which gives me 4. And then I'll just go ahead and say that f of 3 is going to give me an output value of 8. Okay. Let's go back to this. F of 0 would be 2 to the 0th power, and anything to the 0th power as 1. Then if we evaluate f of -1, this would be 2 to the -1 power. Now again, you may need to go back and study your exponentials to practice this, but remember that this is the same thing as 1 over 2 to the first power, which simplifies to be 1/2. Similarly, this would be 2 to the -2 power, which simplifies to be 1 over 2 squared, or 1/4, and this value here would be 1/8. So now I'd like to go plot these ordered pairs that we just found on our coordinate system. So for example, we found that 2 to the first power was 2. There was that first order pair 2, 1 that we get from this information. 2 to the first power was equal to, oops, I've misplaced my ordered pairs, folks. Let me switch those back. 2 to the first power is equal to 2. That's that ordered pair right there. 2 to the second power was equal to 4. There's the ordered pair 2, 4. And 2 to the third power was equal to 8. So there's the ordered pair 3, 8, where we think of this as being 2 to the third. That's how we got that. Likewise, we said that anything to the 0th power, including 2 to the 0th power, is 1. 2 to the -1 power, we said, was -1/2. And I'm just plotting these points as we evaluated them just a moment ago in our table of values. So for example, 2 to the -3 was equal to 1/8. It might be a little bit hard to see in this video, but you should be able to see on your pre-work that I've got nice tick marks there for you to help in the sketching of these. So now I'll go ahead and sketch the graph. I might have to pause the video to get it to look nice, but let's go ahead and give it a shot. And so here we have the graph of the function 2 to the x power. I'm not going to win any awards for that drawing. It's kind of hard to draw it so big, but I wanted you to be able to easily plot these ordered pairs, including these fractional ones, which are a little bit harder normally to put on a graph. Okay, so there's the graph of 2 to the x, and hopefully this is not your first time graphing an exponential function, but if it is, well, This is how we can do it. And what we'd like to do is in subsequent lectures, we're going to speed this process up, where we don't have to sketch this entire table of values. Instead, when we see the function 2 to the x, we'll already know that it makes this generic exponential shape, and we'll see that in the next video. But the next thing I want us to do is I want us to go ahead in number 4 here to construct the inverse function. Okay? We already know what the inverse of exponentiating is. We saw that in earlier pre-work, but even if we've forgotten, let's just go ahead and use our general knowledge of working with inverse functions. So, for example, let's go back to this ordered pair that I've underlined, that 2 to the first power was equal to 2, so we had the ordered pair 1, 2 right here. Well, in our method of constructing an inverse function, notice that because 2 to the x is a one-to-one function, it passes the horizontal line test, it then makes sense to say, we'll define the inverse function to take the input value of, I'm going to come down here where I've got a little more room, to take the input value of 2 and to spit out the output value of 1. So I'm going to go for the inverse function here. We'll do it in a different color. In fact, let me change this. So for the input value of 2, we will have an output value of 1. And what I want to point out here is that these two pairs are connected to one another. This is the ordered pair 1, 2 on the original graph of f of x equal to 2 to the x. And this is going to be an ordered pair on the inverse function. Here we have the ordered pair 1, 2, the ordered pair 2, 1. So what I'd like to do is let's just go through, and just using our knowledge of inverses, let's go ahead and give all the other ordered pairs. So for example, when we plug in 1/8 to this function, it ought to spit out a range value of -3. When we plug in 1/4, it ought to spit out a range value of -2, etc. So then I've gone ahead and constructed all of these ordered pairs that are going to be on the inverse function, and we could go label some more of them. For example, here's the ordered pair 1, 0, so let me plot that. There's the ordered pair 1, 0. A little bit harder to see, we're going to plot the ordered pair 1/2, -1. So there on the x-axis is the tick mark 1/2, the y value -1. So there's the ordered pair 1/2, -1. And let's plot the rest of these. Let's see here. So for example, this would be the ordered pair 8, 3. Because the ordered pair 3, 8 corresponded to 2 to the third power equals 8, for this inverse function that we're constructing, we'll have the ordered pair 8, 3. So now I can go ahead and maybe I can construct the graph. And this is why this point plot method generally is not a sufficient way to graph. But in this case, because I've seen this graph a few times before, I think I've got enough information to be able to plot it, giving it my best shot there. And so here's the graph of the inverse function, f inverse of x, to the original function, 2 to the x. And so we saw in a previous pre-work, and again, folks, this is the most important one to make sure you go back and watch in our introduction to logarithms if you're rusty on this, that how do we describe this inverse function? And we call it the log base 2 of x. So there's the log base 2 of x. And as we saw in our previous discussions about inverse functions, you see that these inverse functions have this nice symmetry about the line y equals x. If I were to take this point right here, 3, 8, and reflect it over the line y equals x, I'll arrive at the ordered pair 8, 3, which is the point that's on the inverse function. Okay, so let's go ahead and summarize what we just did there. We saw that, and maybe you believe me, we took values, we took negative values for x, we took 0, we took positive values for x. We could also take fractional values for x. So for example, although we didn't do this, we could have evaluated this function at 1/2. We'd have f of 1/2 is equal to 2 to the 1/2 power. That's the same thing as the square root of 2, which is decimally approximated at 1.41. And we could even take irrational numbers. We could plug in other values here, and we could plug in any number we wish, basically is what I'm saying, into our 2 to the x function. And that's what we saw through our development of the properties of exponents. So we can now state the domain of this function 2 to the x, either by thinking about what were we allowed to plug in for x into our table of values, which is all real numbers, even though we particularly selective about which ones we picked in. Or we could go ahead and look at the graph of our 2 to the x function. Now, sometimes something that's a little bit confusing is, notice if I were to go out to, say, 8 for my input, I'd have 2 to the 8th, which is a very large number and not on my axes. But it is true that if I go up high enough, my graph, although it may not look like it, will eventually go as far to the right as I wish. All of that is long and short to say that the domain of the exponential function is minus infinity to infinity, and the range we saw was from 0 to infinity. So one way to see that in our notion of domain and range is if I were to, the fancy phrase is if I were to project this red graph or this magenta graph down onto the x-axis, which x values would have x values associated with them? It would be all x coordinates. That's why we said the domain was all real numbers. If you were to look at projecting this graph onto the y-axis, that would tell us about the range. And notice only positive y values have points that get collapsed down onto that graph, which is why we're saying the range is 0 to infinity. A couple of easy points to plug into this were the order pair 0, 1, as well as the order pair 1, 2. So this was 2 to the 0th power was equal to 1, and 2 to the first power was equal to 2. Notice that this graph, we're not going to get into a full description of this or discussion, but this graph has a horizontal asymptote at y equals 0. So that's all information about the function 2 to the x. If we look at its inverse, well, we already know some of this information. For example, we know that the range of the inverse function will be from minus infinity to infinity because of that domain range flip-flop that we do in constructing the inverse. And you can go ahead and see that from this graph. If you were to project this blue graph onto the y-axis, and careful here, this graph does eventually rise as I go far to the right. If you were to project this blue graph onto the y-axis, you would see that every point on the y-axis would have something collapsed onto it, and so the range is minus infinity to infinity. Likewise, we can go ahead and say that the domain of the log function is 0 to infinity. By the way, this gives us this new idea that you can only take the log, you can only take logs of positive numbers. Okay? You can't take the log of 0. You can't take the log of any negative number. And you can see that from the domain range flip-flop we have between constructing a function and its inverse, and there are probably other arguments that we could make to say why we can't take the log of a negative number. So some easy points that are on our log curve would be the order pair 1, 0 and the order pair 2, 1. So notice that this graph, the graph of the blue graph, the graph of our log base 2, has a vertical asymptote at x equals 0. So it has a vertical asymptote at x equals 0. Folks, I didn't do this when originally sketching these two graphs until we had a chance to talk about it, but I do ask that if your graph has a vertical asymptote or a horizontal asymptote, that you go ahead and sketch it with a dashed line. It's a little bit hard to see these when they land on the axes, but go ahead and label that asymptote at x equals 0. Likewise, I'm going to go ahead and label this asymptote right here with a dashed line along the x-axis. That's the horizontal asymptote that the 2 to the x function has at y equals 0. Okay. So the above table actually holds for any exponential logarithmic functions in the form, we could write it, the first one as, for an exponential function, we could write it in the form as log of x or as a to the x, and for the logarithmic function as log base a of x. And you should note that because anything to the 0th power is 1, we will always have the order pair 0, 1 on the graph of an exponential function prior to any transformations, and we will always have the order pair 1, 0 on the graph of any log function. Okay. Let's take that in mind here as we do this last sketch.